Good morning, everybody. And I think it's also, the last lecture which we reached through this cartoon number 7, you reached this amazing conjecture of ADS-CFT correspondence. And so basically we have two descriptions which come from matching the open string picture and matching the closed string picture. So in the open string picture, we know that we can have the open strings ending on D branes, the Dirichlet branes. And so this gives rise to something like non-abelian gauge theories if you start putting these branes together. And so we will have NC number of these branes, and then depending on where the string actually can end or whatever, you get an extra index, and that extra index happens to be this Yang-Mills index which you have there. So now it's obvious that if you have NC branes, you have something like NC square possibilities. And so your gauge field, your vector field A mu, which carries these indices, it will be a matrix where this can take NC possibilities, this can take NC possibilities, and so the gauge fields here will be massless, and they will be matrices, NC square matrices. All right. So now, if you consider low energy limit in this case, then what happens is that you only excite these massless modes, and that's why you only consider these massless gauge fields. Of course, in principle, there are these higher vibrations of the string as well, but they will be very massive, and you just neglect them. What can happen is that, of course, you can also have some closed strings moving in this Minkowski space or whatever, but sort of the modes which are confined to the brane are very far away from whatever is happening, like in this Minkowski space there, and so you sort of decouple these modes from there. So whatever is happening here has nothing to do with what's happening there. So you can sort of neglect, these extra modes in the Minkowski space. So now in this case, your theory is simply characterized by two dimensionless parameters, by the NC, the number of colors of your SUNC theory, and by this Hopf coupling, which is again, it's a dimensionless quantity, which is given by G Yang-Mills square times NC. And so this whole picture is valid when this Hopf coupling is much smaller than 1. So what I derived yesterday is that if you consider in this other picture, if you try to calculate or if you try to argue what is the Newtonian potential behave like, it actually behaves, it's proportional to this Hopf coupling. So if you have lambda much smaller than 1, then gravity is not important, and you can have this picture here. On the other hand, you have the other picture. If lambda is much greater than 1, then you have very massive branes, and you can treat them as classical solutions in this type 2b supergravity in 10 dimensions. And if you are interested in what's happening close to the brane, or you zoom on the horizon of these branes. These branes are extremal branes. They are like extremal Reisner-Nordström solutions. And we know that if we zoom onto the horizon, we discover this infinite throat, where, however, the geometry is super nice. It has enhanced symmetry. There's an ADS5, cross S5 geometry there. And so this ADS5, so the throat has ADS5 cross S5. And it happens that both of these things have the same radius. And so both of these have radius L. So which is like, in this case, it's like a cosmological constant. In this case, it's like the radius of the sphere, right? So you have imagined cosmological constant for your ADS5. So suddenly you are in ADS space. There's like lambda, negative lambda there. Although, the solution has nothing to do with lambda. So the solution is just, the extremal black hole in 10 dimensions and no lambda there. It's just electromagnetism, 5-dimensional electromagnetism, 5-rank electromagnetism plus gravity. So it's Reisner-Nordström solution, but lambda emerges as you zoom onto the throat. And so in that throat, what can happen is that you can have like all possible excitations of strings, and so you can have like full string theory there. And of course, string theory will be again characterized by this GS coupling here. It's also characterized by LS, but we also have this radius of this ADS5 or an S5, And so you can form a dimensionless quantity, L over Ls. So now we have two dimensionless parameters, and they should be related somehow to these two dimensionless parameters. Okay, so now why this is an interesting conjecture is that the two theories, as we derive them, well, these two descriptions are varied in very different regimes, right? So you have this open string picture, is this open one, and you know that whatever we are saying here is valid for lambda much smaller than 1, right? So that's what we derive. On the other hand, we have this closed string picture, and whatever we are saying here is valid when we are using this classical supergravity solution as lambda greater than 1, okay? So now we are saying, well, the duality is saying, well, hopefully, everything will be true for any value of the lambda. So we have this description here. We say, well, it should be somehow equal to that, but that should be valid for any lambda. So if I fix lambda, it should be still, and I don't consider just these two limits. And this is not obvious at all, right? Because you have two very, very opposite regimes, and it's not clear that it should be valid for any value of lambda, but nevertheless, that's what the conjecture is, right? And sometimes you can verify this, and sometimes, but there's no general proof that you can do it, okay? So just to be very clear that this is still even, so this is not a derivation of ADS-CFT, it's just a motivation because, the two pictures are valid in very, very different regimes. And so it doesn't prove ADS-CFT. It can just motivate it. All right. Questions? Yes?
How do I get string excitations on the right, in the right picture? Because I have supergravity action. I would say excitations are like some gravitons.
So here I am using like this classical supergravity background, but now I'm saying, well, I allow for, arbitrary high energetic excitations in that throat. Of course, that's not entirely true again, because if you have arbitrary high energy excitations, then of course you destroy the throat and stuff like that. So we have to be careful. But the argument is typically like, whatever, even if you have very high energy excitations here, like from the point of view of an observer who is very, very distant, these will be low energy excitations, right? So because everything gets redshifted as you move away from the throat. By the way, I forgot one thing. Of course, you can have, so asymptotically here, you have also, possible excitations of Minkowski. And so these possible excitations of Minkowski are sort of like the same excitations of Minkowski as there. And people just, and it's obvious that, whatever is happening here, it's infinitely far away from whatever is happening there because the throat is infinite. So these modes here really don't communicate with whatever is happening there. And that's why you sort of like divide by these modes on this side and on that side. And you just conjecture that whatever is happening on the brain is whatever is happening in the throat, right? But it's, I agree with you 100%. If you like high energy excitations, of course you destroy the geometry and you no longer have throat and you no longer have extreme black hole and so one has to be careful there. All right. So here is the hero who came up with this amazing proposal, and he achieved great and horrible things. But he is the hero we should all aspire to be. So now, just let me stress here. So again, I'm saying these are the parameters of the string theory. These are the parameters on the QFT side. And let me stress this again, like here, the string theory, we know it's a theory of quantum gravity. It has gravitons in their spectrum. It's quantum. It's a theory of quantum gravity, right? So you are really connecting a theory of quantum gravity with some specific QFT, and that QFT has no gravity, and that's what's amazing about it, right? And so somehow, as we will show, so traditionally, the ADS-CFT is used as a tool where you sort of limit something, what's happening here, and you consider some classical limit of this quantum gravity, and you know how to calculate these things, and you learn about QFT. But in principle, you could go also the other way around, and you could say that, that this behavior of the QFT defines what you mean by quantum gravity. That's people even go like that, right? So they say, well, I define my quantum gravity if I know what quantum field theory is. But of course, nobody knows what quantum theory is, and nobody knows what quantum gravity is. So that's why it's more conservative to take certain limits, as we shall do in a minute. Okay, so this wouldn't be a duality if you didn't have the exact prescription, how these parameters on the left-hand side translate to the parameters on the right-hand side. And I derived these yesterday, except I didn't give you the factors of 2 and 2 pi and stuff like that. But what I certainly derived was like this GS was related to this G Young-Mills square. So that came from this Dirac-Born-Infeld action. And we did the calculation. We connected, the string coupling. And it's only true in 3+1 dimensions. Otherwise, there would be this LS to P minus 3. So if you considered branes, which are, then it wouldn't be true. And you wouldn't have conformal field theory. But anyway, so we derived this. And so lambda, 't Hooft coupling is just NC times G Young-Mills square. So this is just comes from definition of lambda, right? So that's the first relation. And then I have the second relation, which I also derived yesterday, is that like how this ADS scale versus the string scale, how it can be expressed, and it can be expressed in terms of lambda. So you see that on the left-hand side, you have the quantities related to string theory, GS, and then this ratio L over LS. And on the right-hand side, you have the quantities related to the quantum field theory, the 't Hooft coupling and the number of colors, right? And you can really translate one to another, and that's, that makes the duality. Yes?
Is it weak strings in Unispace?
Is it?
Weak strings, like that.
Weak strings. Let me... just a second, right? So in principle, this conjecture is for any value of coupling lambda, and for any values of the coupling. But now, okay, few remarks before we go there. What you just asked. So I was already saying this. This duality means complete equivalence of the two theories. Duality means I can change variables from one theory to another theory. I have a direct prescription how to change degrees of freedom on one side to another degrees of freedom on the other side. Here, this prescription is not known. So you don't know how to translate these gravitational degrees of freedom on string theory side to the quantum field theory degrees of freedom. And as I say, the conjecture is a conjecture, it's not proven. It was motivated by the string theory picture. You can argue that something more general has to be true, just by just doing some counting of degrees of freedom and stuff like that. But there's no general proof, and it's just supported case by case evidence. You missed our hero. Okay, I'll show you the hero again. Very, very important. The most important thing in the course. All right, so that's first remark. So now insanity check, right? Can this work? Is it possible that it works? So let's just match the symmetries, right? So we know that on the string theory side, we have very symmetric spaces. We have AdS5 and we have S5, right? So now you probably know that the symmetries of S5 is just SO6. So that has that many symmetries, rotational symmetries. You can rotate the sphere. And AdS5 is sort of like screwed up sphere with just strange signature, if you want, right? So it has something like SO6, except now it has SO4, 2. This stands for the signature. Otherwise, it would be SO6, but AdS5 is something like sphere, but with weird signature. We will see shortly. Okay, so really the symmetry on the string theory side or gravity side is SO4 2 times SO6. So now this better be true on the super Young-Mills theory side as well. And indeed it is so. So you had a course on CFT, and you probably know that CFT in 4 dimensions has precisely this symmetry SO4 2. So now, this is related to the fact that CFTs have, apart from Poincare symmetries, you have also the scaling symmetries, and you have special conformal transformations and stuff like that. So we'll actually have 15 generators in 4 dimensions, and the symmetry is SO4 too. So now what is perhaps more mysterious here is this another SO6 symmetry. And that another SO6 symmetry comes from the fact that our CFT, this super Young-Mills in 4 dimensions, remember it had, the field content was a mu, but we also have these scalar fields phi I, and there were 6 of them. And the Lagrangian is completely symmetric, among these fields. And so what you can do is that you can do, you can rotate these one to another, and then nothing changes. But because you have 6 of them, you have actually extra SO6 symmetry by rotating this one to another scalar field. And so that's where this other SO6 comes from. Of course, why we have 6 scalars is that we have 3 plus 1 dimensional branes. We have 3 branes, right? So then our vector field will be 4-dimensional one, a mu, but then 10 minus 4 is 6. So we have 6 of these Dirichlet directions precisely corresponding to these 6 scalar fields there. Okay, so everybody happy with this? So at least the symmetries match. I know this should be possible, right? Whether it's really true or nobody knows. So now, another amazing thing about this duality, it is sort of holographic. So not quite. You see, we are relating something which lives in 3 plus 1 to something which lives in 10 dimensions. Yes?
Shouldn't there also be a sense in which we can match the gauge symmetries?
Sure. You can start matching all, yeah.
But then for the SUN, you have different symmetries, no? As you change.
So SUN. Are you asking why SUN and not UN, or?
No, like what is the? I mean, the gauge symmetry on the gravity side should be something like.
Yeah, you need to match these. Well, I forgot how this works. We can discuss later. But it should work. All right, so it's holographic in the sense like you are relating something in 4 to 10, right? But what happens is that you have this S5, and this S5 typically not interesting. Okay, so this is typically boring. And you can, Kaluza-Klein reduce on this S5 and whatever. And so then what you are left with, is this ADS5. And so then, as we shall see later, this lecture hopefully, is that you actually have like a nice Minkowski space or nice space for these quantum field theories at the boundary of ADS5. And so then you could say that basically the super Young-Mills lives on this boundary of ADS5 if you neglect the sphere. And that's what typically people do, right? Neglect. Well, you reduce on the sphere. So that's why it's holographic, right? So it's like really everything is captured by this QFT on the boundary of ADS5. I'm saying this very, yeah.
But can you reconstruct the sphere in the context of the correspondence?
Certainly the sphere will be encoded in things. Again, I would have to remind myself how this works, but sure, yeah. You have to do this, Kaluza-Klein reduction on the sphere, and of course that has some imprints on it. Yeah. So
I think NC is always large in this conjecture. You're taking the large and the limit keep lambda fixed. So
you're taking large and
match on the gravity side. You don't need to match SU3, SU4, SU5, but it's always.
But it says complete equivalence somewhere. Complete equivalence means for every eye. Right.
Yeah, exactly.
No one knows how to do it, but in principle.
At every lambda. It's different.
No, for every parameter, yeah. All right. Let me now do something weaker, okay, and weaker. So this is, again, the formula which you have seen, how to relate this GS and L over LS to lambda and NC. But people typically, because, you don't understand what's happening on the quantum gravity side, and you don't understand what's happening on the QFT side, except for some perturbations. So that's why people take this, nice limit where they say, well, I can approximate my string theory by weak gravity. Okay, so we are asking when classical supergravity is actually valid on one side. Okay, and so you have two conditions here. So one condition is that the strings are rather small. So LS is much smaller than this L, which is another scale we have, and so it's like point-like strings, right? So that's the first condition. So we require that L is much bigger than LS. And if that is true, and you look at the formula, the right formula there, so immediately it tells you that lambda must be really large. Okay, so just you land that lambda must be super large when this. Well, that's how we derive it anyway, right? So we said, well, for lambda large, we will have this classical description of supergravity. That's how we sort of like motivated it, right? So we are returning back to this fact. So that's first thing. Second thing is you may be asking when I can neglect the interactions of the strings, right? So when you have these weird Venn diagrams and stuff like that, you have loop corrections, right? For the strings, they can match and they can form like something like loop corrections. And so this will be, you will suppress these if this interaction constant is very small, GS, for the strings. So we require that one is much bigger than GS. But GS from the left formula is lambda over NC. Okay, so you require that the ratio lambda over NC is much smaller than 1. And so if you put the two together, then you arrive at a magic formula that your classic supergravity will be valid if you have this thing here. So lambda must be much greater than 1, but also NC must be much greater than lambda. Okay? And so what it tells you is that, so this is amazing. So you immediately see that I can study, something that happens on a, weak gravity side, something that happens like from very weak gravity, weakly coupled, and so on. But that would be dual to something that has large lambda and large NC. So large lambda means strongly coupled quantum field theory, right? So it basically gives you, it's a strong weak duality. On one side you have weak gravity in this regime, and on the other side you have strongly coupled QFT. And so this provides you an amazing tool how to study these strongly coupled QFTs by simple weak gravity calculations.
But I thought that lambda over NC is just G Young-Mills, no? So why don't I just make, why isn't the second condition just that G Young-Mills is small?
Lambda over NC is G Young-Mills. Sure, because if it's big, then you have lots of interactions, right? And so like you will have scattering of photons on photons and stuff like that, and then you will not be able to neglect them if that's a large constant. It's really suppressing the loops.
Why are my two conditions G Young-Mills is small and N is large? Like why? I mean, I guess it's the savior.
The question is why we still have strong CFT if G Young-Mills is small, right? Because G Young-Mills is proportional to G string, which is small.
Yeah.
What's that?
Sorry, I'm not following. So this is just to suppress the loop corrections, right?
On the CFT side, this condition effectively means that G Young-Mills is small, right? I guess it's
Yes.
controls interaction, so you still have strong.
It's the lambda which controls the interactions. By the way, if you don't like this condition here, you may be asking a different condition. So standardly, if you ask a person who's doing gravity, like when you can suppress the quantum gravity corrections from the point particle point of view, and so note also that like the standard gravity, quantum gravity criterion is that whatever the scale of your problem is, so we have the geometry which is characterized by this length scale L, and you would say that quantum gravity quantum gravity effects can be neglected if your scales, the curvature scales and stuff like that, are much larger than Planck length, right? So you would say that L over L Planck is much greater than 1. That would be the standard thing which you could ask. So now this is slightly different criterion than what we are imposing here, but let's see what it would give us. So in principle, well, let's do L to the 4, L Planck to the 4, magic number. If this is large, this would be also large. But what is this, right? So now if you are using that formula there, you see that this is like, if I use the right formula, so L to the 4 is Ls to the 4 times lambda. So Ls to the 4 times lambda. And then I told you at some point that you define G10 to be L Planck to the 8. Right? So what stands here is G10 to 1/2. So that's L Planck to the 4. Okay, and so now you use left formula, and you have GS and C, which is lambda Ls to the 4. So this thing here from that left formula is lambda. And then G10, we had a formula how to relate G10 to GS square Ls to the 8. So if I take square root of that, it's GS Ls to the 4. Right? And so now you see everything nicely cancels, and you find that this is NC. So if you want, this standard quantum gravity criterion would give you that this ratio here must be much, much larger than 1. And you are again concluding that this is only possible if you have large number of colors. Right? So just to give you like something, like I would write down this thing here immediately, and so that gives you the same conclusion. So anyway, what we'll be doing basically, well, how this thing is typically used is that you take both lambda and NC to infinity, right? And so that certainly this will be satisfied. If you take lambda and NC to infinity, NC will be much bigger infinity than lambda, but that doesn't matter. You take both of them to infinity, and then you'll be looking at the corrections in 1 over NC and 1 over lambda, right? And so this gives you like a different expansion if you want. So it's a different expansion how you do your perturbations. It's in 1 over lambda and 1 over NC. Questions? Amazing, right? So okay. So now you've taken a course, but let me just spend 5 minutes on what is conformal field theory, because that's what's actually there. And so you know it's just a special quantum field theory with bigger space-time symmetry, right? So in particular, this theory will be invariant under conformal transformations, which is a generalization of Poincare transformations. So we now allow transformation x mu to x mu prime, such that the metric actually need not to stay the same, but it can pick up this prefactor omega square. Okay, and so of course that means that you have more possible transformations than you had for the Lorentz group or for the Poincare group. So in particular, this will be true for the Poincare group, where omega is equal to 1, but you have extra possibilities. And so you have these special conformal transformations, but most importantly, you have these scaling. So now I can scale time and space, lambda t and lambda x, right? And so that will produce some omega, and you will study this in your tutorial but you have already seen that in the previous course. So this is an extra transformation I can do. And if you do this, and at the same time, you transform the fields like that, where you call this delta thing here the scaling dimension, and if your action remains invariant or whatever, then you have this scaling symmetry for your theory. So now, of course, similar to what happens with the Lorentz group, now I can characterize my particles with the momentum and spin and whatever. You also have to provide what this delta is. So you also have another scaling dimension, which is another number or another thing which characterizes your field. And you've probably seen this theorem is that, conformal field theories are still interesting. And basically, the conformal symmetry is the largest one you can still have for interesting quantum field theories. And I'm sure this was discussed in the course. Okay, so that's one primer. Another primer is that, you can have examples of conformal field theories, which is like Maxwell equation or massless Dirac equation or classical lambda 4 theory or classical Yang-Mills. So there will be examples of conformal field theories. At the classical level, so whether you have also this preserved at the quantum level depends on whether the beta functions are 0 or not. And they will be 0 for the first two, but they will not be 0 for the latter two. So at the quantum level, the last two are not. You break the conformal symmetry. Now let me repeat also this. So you know that the correlations will be highly limited. Correlation functions will be highly limited by the conformal symmetry. And so you already know that, for example, in this Poincare symmetry, if you have Ox or Y, 2-point function, then it, by Poincare invariance, it must depend only on the difference between X and Y, right? But now you have an extra symmetry and it has to be 2 delta there, which is the scaling dimension. Finally, conformal field theory has actually interesting applications. First of all, if you want to study phase transitions in statistical field theory, then you know that second-order phase transitions are described by conformal field theory, and actually you can relate these critical exponents, it's like what's happening in the second-order phase transition, to the scaling dimensions delta. By the way, which actually brings me to a question which somebody asked me. I still don't know the answer, but maybe you will immediately know the answer. Like I told you that we have these charged black holes in ADS, and they can have this interesting van der Waals behavior. And at some point, you have a critical point there where the phase transition is second order, right? So we had the phase there. So what does that mean? Does it mean that at that point I'm restoring somehow conformal symmetry, or what does that mean? So that's a question to think about. So we had this diagram of the free energy, and we had the swallowtail, and the swallowtail was diminishing as we were changing the parameter. And at some point, we had this critical point where the phase transition was of second order. What does that mean? So you have now a classical space-time, charged ADS black hole, certainly not an ADS space-time. You have non-trivial black hole with some tuned charge with respect to mass and stuff like that. So the question is, what is so special about this point? Can you relate it somehow to conformal symmetry? And I don't know. So please tell me if immediately you come up with an answer, okay? And then we write a paper. Okay. So very good. So we have these phase transitions, especially second-order phase transitions. String theory is a conformal field theory. So we have this Wiles symmetry, and so it's definitely useful for studying string theory. And then what Jaume probably told you is that like you have the space of quantum field theories, and if you have like the fixed points of your RG flows or whatever, then that's where your CFT is. And so knowing about CFT, and then you can do the perturbations around CFT, and then you also like studying what's happening with the space of the theories around. So it's very useful to at least understand this enhanced symmetry field theories if you cannot understand fully the full QFTs. Right? So we have seen all of this, right? So I don't need to. Great. Questions? So now, the second question is, what is ADS? Right? And so I already told you, so it is a maximally symmetric solution of Einstein equations with negative cosmological constant. So now what is quite annoying about ADS, but it has like, you can write it in many coordinate systems, and each coordinate system is useful for something. So what I would like to discuss first is this embedding perspective. And that embedding perspective is really very useful for recognizing the symmetries of the ADS space. Why it's maximally symmetric? What does that mean? So maximally symmetric means I have the most number of Killing vectors which is possible in a given dimension. Okay, so it's like Minkowski is maximally symmetric if you have flat space, but ADS is maximally symmetric, has the same number of Killing vectors as Minkowski space, but it has no negative cosmological constant. All right, so embedding perspective. So what do? Is basically you describe this ADS space as a hyperboloid living in some very weird space with 2 times. So what we have there is this R to 2D minus 1. So we are describing ADS D space. So we are in D dimensions, and we'll be describing it like we take a D plus 1 dimensional space-time, and we put a hypersurface in that D plus 1 dimensional space-time. It will be a hyperboloid, and that's what the induced metric on that will be our ADS space. Okay, so we have RT to D minus 1, meaning we have 2 times. So the metric here is like a Minkowski metric, but now with 2 times. We have y minus 1 is 1 time, and y0 is the other time. Okay, so I just described that by putting this eta AB metric with 2D minus 1. So this is a D plus 1 dimensional metric with 2 times. So now that's your space-time where you embed your ADS space, and now you describe your hypersurface there, your constraint. Other constraint is like you have minus L square. L is the ADS radius, right? And then you take again this eta AB, YA, YB. Okay, so that's how you do that. So now, of course, you can play with other possibilities, right? You can play, what if I don't do R2D minus 1, but I just do R1D minus 1, or whatever. So you would have normal Minkowski space-time, and you will be embedding something. It will be also interesting and useful most of the time, right? Or you can be asking, what if I put a plus here? So what stands here in this minus L squared, this minus? It stands like so it's like a negative radius thing. So if you put positive radius thing, you will get de Sitter space and stuff like that. So if I put a plus L square, I will have positive, what is it? Curvature, or is it curvature? Okay. Well, anyway, so various possibilities are possible. Okay, so you just playing with this 2 and D minus 1, you can do 1 D minus 1 or 0 D plus 1 and stuff like that, and you can be choosing random pluses and minuses on the left side, and it leads to normal sphere, to hyperboloids, to de Sitter space, to Minkowski space, and stuff like that, right? So I'm just using this one particular one here, but you immediately see that because we have 2 times here, something is very, very wrong about ADS space, right? Because you are embedding something with these 2 times, so 2 times are typically bad, and you cannot go more than this 2 times. Anyway, so what you do next is that, of course, you solve the constraint, right? So I solve the constraint, let's say, for y minus 1. Let me attempt that. So if I'm solving the constraint for y minus 1, I will have y minus 1 square is equal to, now I put L square on the right side, so it will be L square plus, and then it's all these y minus y0 plus y1 plus yd minus 1 square and so on. So what stands there is like really eta AB, the normal Minkowski one, 1 d minus 1 ya yb, and then square root of that. Right? So this is how I solved this constraint. I just solved it for y minus 1, solving that thing over there. So then I have to calculate what is d of y minus 1. And of course, this will be like 1 over square root of this. And this is just a constant, so that will not make any trouble, but I just have to differentiate that. And so it will be eta AB ya d yb. So I have 1/2 coming from the square root, but I have 2 here, and they are the same, so it will be like that. Or you just lower this index, ya, with this eta ab, and this is just 1 over square root ya dy a. Okay? So now you take that, you take the thing, and you plug it back into your metric. Right? So then your ds square, your ds square will be, this thing here, which is like 1 over square root ya dya square with a minus sign. It's a minus sign. And then you will have the rest. The rest is like dy square and whatever. So that's just the standard thing plus eta ab dy a dy b. Right? That's what remains there. And so you immediately see that if you want to write your metric, so this induced metric on this thing here, well, it will be this thing here, eta ab, and that it will be minus, and then if I square this, I will have ya yb divided by, and then I put the square root here, and the square root is just L square plus ya. Okay, so this is my induced metric here, and that's the ADS metric. Okay, so it's easy peasy to do that, and this is the result. So our metric on ADS space can be just written in this embedding thing like that, where I defined the index down by lowering with this normal Minkowski metric. Okay, so now you take this metric and you use Mathematica or Maple or whatever, and it calculates you the Riemann tensor, and you'll find that the Riemann tensor is proportional to GG minus GG, which stands for a maximally symmetric space. Okay, if it's 0, then it's Minkowski. If it's non-zero, it has this negative curvature here. It will be ADS. If it's plus 1 over L squared, it will be ds. Okay, but it's like, this GG minus GG is dictated by the symmetries of the Riemann tensor, so you know that it has to be antisymmetric in A and B. So basically what you are doing is that you have A and B, and then, let's do C and D. It doesn't matter. So C and D has to be antisymmetric, so it's obvious that I have C and D here, and then I swap the two, and I have a minus that. So it will be automatically symmetric in antisymmetric in C and D. Okay, so now you have the Riemann tensor, and you can start constructing it. You can construct, the Einstein tensor and the Ricci scale and stuff like that, and you will find that it satisfies these Einstein equations, GAB plus lambda GAB, where lambda is given by this formula here. Okay, so it is indeed a solution of vacuum Einstein equations with cosmological constant lambda given by this radius, which is given by this radius of embedding. Right? Okay. So that's an easy calculation. Everybody happy? Okay, very good. So that's good. So it is a solution of vacuum Einstein equations. But why is this maximally symmetric? Right? But you see that the constraint and the metric in this embedding space, well, they look like Minkowski metric, but it's just with 2 times or whatever. So you know that these things here will be invariant under something like Lorentz transformations. This is that weird signature, right? And so you will have like Lorentz transformations in d+1 dimensions, and they will be there will be symmetries of these, of both, of the metric and of the constraint. And so the induced metric must be also symmetric under all these transformations. Okay, so here we go again. So that's the two things which we need to study symmetries, and then the statement is these will be invariant under something like a Lorentz transformation, lambda AB xb, where now this is a Lorentz transformation with a weird Minkowski metric. Right, so I have this eta AB2 d minus 1, but that's the only difference. It's just this minus sign is the difference between what you have there. And now you can play the same game. You can, just to make it more obvious, you can expand this around 1. So you will have 1 plus more perturbation, lambda AB. And then you can lower this index, and you will find that if you plug this thing here into that Lorentz transformation thing, as you would do normally, you just find that this lambda AB is antisymmetric. Right? So now the question is, how many of these lambda ABs are there? Right? So now, because they are antisymmetric and they live in d+1 dimensions, so everything here is in this embedding space, so in d+1 dimensions. So the question is, how many antisymmetric objects with two indices in d+1 dimensions you have, and there's this combinatorial number d+1 over 2. So we have d+1 over 2 generators, and that's the maximum number of symmetries you can have in d space-time dimensions. Okay? And so this is how you prove that these things are truly maximally symmetric. So if you are in 4 dimensions, you know that Minkowski space will have 10 killing vectors. That's your symmetries. So similarly, ADS4 will have 10 killing vectors. They will be just weird quick rotations of these things. But yeah, it has the same number of generators. And these lambda AB then form a representation. So we are embedding in d+1 dimensional space. So our ADS D in d dimensions has then the symmetry O d minus 1 and 2 coming from these generators. Questions? You have seen this? Or not? Have you seen this? You have? Okay, it's just a repetition. That is great. Okay, so now here's the picture. So let's say I want to show this embedding of ADS2. So what you do is that you embed it into this 3-dimensional weird Minkowski space. So you have y0, which is one time, and then you have y minus 1, which is another time. So these are the time coordinates, like that. And then you have one spatial coordinate y1. That's my embedding space. So we have a space with 2 times, and then with one spatial direction. So now you draw a hyperboloid in this thing, which is and that's the surface of that hyperboloid is your ADS space, right? This is how you can imagine the ADS2 looks like. But you immediately see the problem is that if I draw this line here, like that, so you are only going in the y0 and y minus 1 direction. I am fixing y1. So you are only going in time directions. And so then it's not, then it's obvious that, if you go around that, you are actually moving on a closed time-like curve. And so you can either live with the fact that ADS space has closed time-like curves, and then, if you go in certain directions, you come back, but unfortunately it's a time direction. So you can go back and kill your grandfather and never be born and stuff like that. Or the other possibility is that you say, well, actually, as I go here, I circle around, I come to the same place, and then you say, well, it's not the same place, but rather I keep saying, well, I keep wrapping it like that, and like that, and like that. So I will say, at that point where I come back, it's actually I put a new sheet onto my hyperboloid, and that's called a covering space. So you start winding that around, and then you go to the covering space. And you wrap the hyperboloid many, many times. Okay, so this is the embedding perspective of the ADS space. Any questions about that? It's really useful, this one, that to show the maximal symmetry and to have like an idea how this looks like in this embedding space. Now look at that. We have this. Let me discuss maybe the global one. Now, so you have this y-1 coordinate and y0, which are the 2 times, and then you have the remaining coordinates. So now the other coordinate systems are typically like I have to single out some of these coordinates, these y-1 or y0 or yd-1, and then depending on which I single out, I will have different coordinate systems, which are useful. So let me do first the global coordinates. And what you do is that you precisely single out the 2 times. So you single out y-1 and y0. And you sort of move the constraint to something you know. So what do you do, right? So instead of these y coordinates, you will have now coordinates t tilde and rho tilde and these omega I. Okay. Now you move the constraint. So you have this hyperboloid constraint. So now you move it that these omega I coordinates will be the standard angular coordinates on the sphere. And of course, they satisfy omega I square, omega 1 square plus omega 2 square, and whatever is equal to 1. So these omega. So that's how you move the constraint. Okay. And you know this y-1 and y0 are given over here with these cosine h and sine t tilde and so on. Okay, so as a result, if you plug it there and you use that metric, you find that this is your metric now in these new coordinates. And as I told you, whereas the original hyperboloid was such that you only could go around the hyperboloid once, that will correspond to the fact that this t tilde here would have to be periodic with period 2 pi, right? I'm coming like that and going like that. So instead, if you say I'm putting more sheet on that, I'm going to this covering space. So you now allow these t tilde to go from minus infinity to infinity, wrapping the hyperboloid many, many times. Okay. And if you go to this covering space, well, then you no longer have closed time-like curves because if you unwind it, you just go from minus infinity to infinity, and that's fine, right? So that's what people typically do. They go this covering space and consider this t tilde to go from minus infinity to infinity instead of what was before, and we get rid of the closed time-like curves. Let me do one more thing. So we have this metric here, and of course, it seems like you have this cos h and whatever. So this is very much non-compact. So of course, there will be the rho is like a radial coordinate. It can, so this can be because you have the cosh, you have things. So let's do just one thing. Let's compactify this. Okay, so you can compactify this thing here by saying, well, sine h rho tilde is a new radial coordinate theta, and you do tangent theta is equal to the sine h rho tilde, and then you find that your previous metric prescribes like this. But now this is super nice metric, right? Look at that. So there's some conformal factor standing in front of the metric. But then you have super simple geometry in the bracket, right? So now, the original infinite range for rho now translates to a finite range of theta. So you can go from theta to 0 to pi half in which case you divide by 0 and you cannot extend anymore. Right? So your infinity is now located at theta equal to pi half. Okay, and so now if you look at what the metric is inside, there is time, and then there is something which is, it looks like a cylinder. You have the cylindrical coordinates almost. You have d theta square and sine square theta. So if you had it's like a non-Euclidean cylinder, right? And indeed, that's what the ADS space is that you should be thinking about ADS space like a infinite cylinder. My theta is like the radial coordinate. I compactified my infinity, not going all the way to infinity, but I compactified it to be at theta equal to pi half. So the infinity is called conformal infinity, and the metric on that conformal infinity is I forget about the conformal prefactor for the moment, right? And then I look at what is inside the bracket, and I choose where my infinity is. So I choose this theta equal to pi half. So which means d theta square is equal to 0 and sine square theta is whatever, 1. And then you see that the metric on infinity, at infinity of the ADS space on this conformal boundary, it looks like dt square plus d omega square. Okay? Have you seen this metric in cosmology or whatever? Okay. So this metric is called Einstein static universe. Okay. And it's obvious that it is like you have the time, which is like the R, and you have the sphere. So actually, the boundary of ADS space is conformal, or looks as an Einstein static universe. This is where your field theory will live, in this Einstein static universe. So sometimes people will tell you, I will tell you in a minute, that actually it lives sort of like in Minkowski space, the QFT. So that's like if you zoom on part of this, you will get something like Minkowski. But like the full thing is the Einstein static universe. Yes.
I mean, it's conformally equivalent to Minkowski. Right?
And yeah, so okay, very good. So I haven't discussed this, so let me postpone the conformal invariance and the conformal symmetry to the next slide, okay? Very good. But topologically it's not the same thing, right? So topologically I have Minkowski and I have this thing here, like I have the full sphere. So what you need to do is that you need to remove one point, and then it's the same. All right, so this is okay. Let me show how this picture looks like. By the way, okay, so this is these compactified coordinates, very nice to discuss. What is the boundary and stuff like that. If I do return back to this metric here, so again I am in the global coordinates, but this previous metric with this infinite range for rho tilde, and I do a coordinate transformation on these things here on this rho tilde. Then what you get is that you introduce new rho, which is this rho tilde, and you rescale the time t to tau. And those global coordinate metric, which I showed you before, writes as that, which is what I showed you a long time ago. Okay, so this is like the black hole coordinates as you know them, the usual global coordinates for black holes. You have the metric function f there, and then you have the normal radial coordinate times the sphere, and f is 1 plus r squared over l squared. Okay, so this is the standard global coordinates, which I showed you before. Okay, and so the picture, what you should be thinking about this ADS space is that you have this infinite cylinder, time goes this way, right? And then rho is the radial coordinate, goes from the center of the cylinder to there. Now in this case I don't have the compactified boundary, but the surface of the cylinder is the boundary, and that's where your Einstein static universe is. Okay, and then as you go around, then there is a sphere. So think about ADS space in this way as a cylinder, infinite cylinder, and the boundary is this Einstein static universe, but it's like the surface of that cylinder. Okay. And what is important is that really, this boundary here, it's time-like boundary, right? So that's very, very different from Minkowski space, right? In Minkowski space, my boundary Scri plus or Scri minus or whatever, they are null surfaces, right? And you can get there only if you move at the speed of light or whatever. Here, you have nice time-like boundary, and so it's a nicer space if you want, or more familiar space. All right. So there are many other coordinate systems. I will discuss them next time. So we will talk about Poincare ADS coordinates and whatever. So it's quite annoying with ADS that there are so many of these coordinate systems, but each of them is useful for something else. The embedding perspective is useful for showing the symmetries. The global coordinates are useful for these are definitely useful coordinates. They are like familiar coordinates which for black holes and stuff like that, and they cover the whole ADS. But then you can also sometimes consider some various pieces of ADS, and they can also be useful because the calculations are easier in those coordinates. And I will show them to you next time. So let me stop here, and we continue on Tuesday next week. Questions? Yeah.
Why is time-like boundary better than null?
I'm not saying it's better, but it's definitely more familiar, right? Because if you have normal, Minkowski space, and you want to put a field theory on something that you prefer there's like normal time and whatever. So here you have null surface and everything is weird. Like if you try to put a field theory on this surface, like it's not a normal field theory because you don't have normal time. If you want, the time is null rather than time-like or whatever, right? And so yeah. But people know how to do these. So like there's Carolean physics and whatever. So where you can describe. So basically, this thing here is like a Carolean manifold. If you heard about that, and then you can still, it's still interesting. But basically, like null surfaces require special attention, right? But the time-like surfaces you are very much familiar with. If you consider the de Sitter holography, then of course this is turned to the side, and you would have space-like boundary, right? And then that's even less obvious how you put a field theory on space-like boundary, right? Because you have no time. Yeah. Okay, more questions? Well, have a nice weekend then.